Hello everybody. We have been discussing sequential logic circuit design, synchronous sequential logic circuit design, and we had seen in the previous classes with example how state transition diagram is used to define the problem statement, and then from that state transition diagram we arrived at logic circuit. Okay. So, today we shall look at another way of representing the problem statement, which is algorithmic state machine chart, ASM chart, and we shall look at how what are the basic components of it and how this ASM chart looks like for Mealy model and Moore model. Now, as you understand from the name itself, algorithmic state machine chart is something which is associated with the algorithm, the way we write codes or pseudo codes. So, it is a flowchart like representation. Now, why what is the usefulness of it? So, if you have noticed a state transition diagram, the one that we have taken as example. So, for every state depending on the input, okay, we were having paths leading to other states. Okay. So, if there are one input, we had in those examples say A. So, say 0 to 0 it was here, and 0 to 0 it was here, and then one output was 0, it was going to B. Okay. This was the kind of thing, right. Now, imagine if instead of one input there are two inputs. So, what would have been the cases? So, the case would have been something like this: from A 4 such branches coming out, from B 4 such branches coming out, okay, and the circuit, the state transition diagram would have been very complex and inconvenient to read, okay, and to make out something out of it. And if the number of inputs even is more, so you can understand that for 3 input there will be 8 such paths coming out from one particular state, okay. So, algorithmic state machine gives a more readable kind of representation. Okay. It may be a bit long, flowchart like representation, but it is easier to read, okay, and make appreciation out of it. Okay. Now, what are the basic components? The basic components are, this is called state box. Okay. So, in this state box you have the state name. So, that is there, and for Moore model you can understand the output that will be derived solely from the state that you can write down within the state box. Okay. For Mealy model we will not write anything inside. Next is conditional output box. Okay. So, this is another block, another symbol that we shall be using. So, here we are writing the conditional output. So, output derived from the state as well as the input. Okay. So, this is the corresponding symbol. Of course, it is useful for Mealy model. So, it will not be useful for Moore model. And finally, the important part of it is called decision box. Okay. So, based on the input variable, that input variable x, y, z, whatever. Okay. So, we will be taking a decision. So, the flowchart will move either in the direction of input sampled as 0, or it will go in the direction of input sampled as 1. After sampling we found that the input is at value 1 or input is value at 0. So, one of these two paths will be taken. Okay. So, these are the 3 important components, basic components. Now, let us look at one example where there are more than one inputs. Okay. So, to appreciate the how ASM chart works. So, in this particular example, the problem statement that we have placed is design of a very simplified basic vending machine. Not all the features are there, but some of the basic features are there. So, it delivers only one product, okay, and that product is costing rupees 15. Okay. So, that is what you have seen here, and the machine is such that it can accept only 2 types of coin. One is that is of rupees 5 coin, another is of rupees 10 coin. Okay. And to sense the deposition of coin, the coin that is deposited in the machine, okay, So we have got two sensors, okay, and the sensors are such that I is the sensor which just senses if anything is dropped or not, okay. So if I is 0, that means nothing has been dropped, okay. So that is no coin has been deposited, right, and when I is 1, then if j is 0, right, so that is a kind of sensing mechanism which differentiates between 5 and rupees 10 coin, rupees 5 and rupees 10 coin, okay. So if j is 0, then rupees 5 is deposited, and j is 1, rupees 10 is deposited. Is it fine? Okay. So what is the other thing important here is that it has got two output, okay. So one output is whenever you are customer is depositing the coin, whenever rupees 15 is reached, okay. So one output x is made 1, which is otherwise 0, okay. So that accentuates, that actually energizes maybe a spring or a magnetic coil by which a product which is kept in a spring loaded manner, so that is getting delivered to the output, okay, output placeholder, right. So that is x, right. Another output is there which is y, okay. If by any sequence the machine receives rupees 20, say rupees 10, and then again rupees 10 has been deposited, because 2 coin of rupees 10 was there with the customer, okay. So in that case, other than the product, rupees 5 need to be returned. So that is what your y is. So y is otherwise 0. When y becomes 1, okay, then rupees 5 is returned, okay. So there is a particular place where a stack of say rupees 5 is there, so some spring goes out and then rupees 5 comes out and it is again returned to the customer, okay. So this is the way the machine has been is to be designed and is expected to work, okay. So these are the two inputs, right, I and j, and the outputs are x and y, okay. So now let us see. So for that we are beginning with the state definition, okay, and we also plan to work out a Mealy model, okay. So Mealy model, so the first thing that we decide is A is initial state, that is no money has been accumulated, okay. So money available with the machine is 0, this is the initial state, right. B is rupees 5 has been received, C is rupees 10 has been received, okay. Rupees 15 is not required because it is a Mealy model. Whenever rupees 10 is there, if it receives rupees 5, it will deliver a product. If it receives rupees 10, it will deliver a product as well as rupees 5 will be returned. And at B, if it receives rupees 5, okay, that means it is going to next state, that is C, and if it is receiving rupees 10, okay, it will deliver a product and come back to the initial state, okay. So that's why rupees 15 is not required, okay. Is it clear? Now since it is Mealy model, right, so we begin with the very first step. So after the start, the beginning initial state is A, okay, that is no coin has been deposited, and the digital circuit, the clock that is there, that could be much faster than the human customer who is depositing the coin, right. So there may be many such clocks going on by between two successive deposition of coin, okay, deposit of coins, okay. So this so there will be a case that it is sampling the I whether a coin is deposited or not, okay. So it will find that this is 0, no coin has been deposited. So what should it do? It should remain in state A only. Is it okay? So that is the path it is showing, and this is the conditional output box. If it is at state A and no coin has been deposited, of course output should be, both the output should be 0. Is it fine? Okay. So that is, and if it is 1, so some coin has been deposited. So we have to take a decision right, or the machine has to take a decision. So we shall see that, at that time, if it is 1, then it need to look at what is the whether it is j is equal to 0 or j is equal to 1. So another decision box will come. Okay, right. So this is what you can see over here. So at A, I is equal to 0. If it is 0, it is output, of course, is x is equal to 0 and y is equal to 0, it remains at A. But if it receives 1, if it senses, it finds that it is 1, okay, then some coin has been deposited. So depending on j, whether 0 or 1, it will be rupees 5 or rupees 10. So if it is 0, it is at state A, rupees 5 has been received, no output. No output means no product delivery or rupees 5 return. So that's why these two are 0, 0, okay, and it goes to B, that is rupees 5, okay. So this going to next state is synchronized with the time. So A is there for one particular clock cycle, and then next clock trigger it goes to B and it will be there for one clock cycle, okay. Similarly, when it comes, if it is 1, okay, so it is rupees 10, A 0 and rupees 10, still it is not a case of delivering the product, so no product is delivered. That is what you can see over here, okay, and it goes to state C, it goes to state C, okay, which signifies rupees 10 has been received. Is it fine? Okay. So next, what will it do? It is either in state B or state C if one coin is deposited. So we shall examine each of these states, right. So if it is at state B, consider that rupees 5 has been deposited just before it. So it is at state B, okay. So we are following this path. So we are following this path, we have come here, right. Now, as I said, human response is slower than the machine, the clock, that is what is expected here, okay, that is usually what you will see, okay. So there will be cases before the next coin is deposited to get the product. So it will find that no further coin has been deposited. The earlier coin that has been deposited, that has been taken away, of course, in that particular place where the sensing mechanism is there, okay. So this is 0. Right, I is equal to 0. So that means no coin has been deposited. So what will happen? So it will remain at state B, okay, and no product will be delivered, right, or no coin will be returned. So that is what you see here, x is equal to 0 and y is equal to 0, right. But at state B, if I is equal to 1, that means a coin has been deposited, then there are two choices. Okay, for j is equal to 0 and j is equal to 1, two things will happen. Okay. Now if j is equal to 0, that means earlier there was rupees 5 and another rupees 5 has been received. So rupees 10, still it is not the case of delivering a product. So x is equal to 0 or y is equal to 0, or rupees 5, of course it is not reached rupees 20. Okay. So rupees 5 and rupees 5, now it is rupees 10, so it has to go to state C. State C signifies rupees 10 has been received, isn't it? Okay. And at state B, okay, when rupees 5 was there, if I is equal to 1 and j is equal to 1, what does it mean? Rupees 5 and rupees 10 has been received. Okay. So that is a case of delivering the product. So that's why x is equal to 1 and y is equal to 0. And after that, what will do? What will the machine do? So the machine will go back to its initial state. Okay. So that next time the same customer or another customer deposits appropriate amount of money, okay, another product can be delivered. So that's why it is written to state A. Is it fine? Okay. So we shall examine now what happens when it is at state C, right? So when it is at state C, right, that means rupees 10 has been received so far, right. Again, there could be cases few cycles before the next coin is deposited, okay, no coin is sensed in that particular placeholder where the coin is going after being deposited. Okay. So, this I is sensed to be 0. Okay. So, no product is delivered and it is remaining at state C, fine. And if I is equal to 1, right, then either rupees 5 or rupees 10 has been deposited, which depends on J. So, again a decision is to be made based on J. Okay. So, if J is 0, what does it mean? Rupees 5 has been deposited. So, rupees 10 was there and rupees 5. So, rupees 15 has been received. Okay. So, within that clock cycle itself, right, the product x is equal can be delivered by making x is equal to 1, right, and y is equal to 0, and it goes to state A. But at at state C, whether you go via a deposit of rupees 10 coin or rupees 5 and rupees 5, after that you are depositing a rupees 10 coin. Okay. Order does not matter. From C, if you find a rupees 10 coin has been deposited, so what is the total worth of what has been these coins? So, total value is rupees 20. So, product is delivered and a coin is returned, a rupees 5 coin is returned, okay, by making x is equal to 1 and y is equal to 1, and then it goes to the initial state to deliver the next product. Okay. Is it fine? Okay. Now, if you bring all those components together, so this is the full ASM chart of that machine that we have just discussed. Is it fine? Okay. So, compared to state transition diagram, it is less compact, you can say. Okay, that was more compact and all, but you can see it is more readable. You can logically move from one particular instance to another, one particular state to another state along with time. Okay, and with those decision boxes, you examine what are the inputs, and based on that, either you deliver the output or do not deliver and move to the next state. Okay. So, that gives a flowchart like, or as I said, algorithmic representation. Okay. Fine. So, we would now like to see the this mood model, how it will appear in the ASM chart, right. And for that, let us consider the example that we had seen before. Okay. So, it will be easier for us to compare with the state transition diagram also, right. So, the example, if you remember, we have to detect a sequence 110 from a binary data stream. Okay. So, there is only one input. Okay. So, for this one input, we have named it x, right, fine, and then again what will you and the since it is a Moore model, output will be generated from the state, right. So, conditional output box will not be required. So, this kind of this symbol will not be required, okay, and the state output will be written within the state box, right, that we discussed as in the first slide, in the basic component related slide. Okay. Right. So, initialized with state A, that is no bit is properly detected. So, the state definition remains the same as was the previous discussion, okay, as was there in the previous discussion. So, it is state A, and at that time output is 0. So, no bit is properly detected. Okay. So, y is 0. So, y will be 1 when all the 3 bits are detected properly, fine. Okay. So, then it is looking at x. So, if x is equal to 0 and if x is equal to 1, now it is synchronized with the clock. So, this input this data that is coming is synchronized with the clock, right. So, x is equal to 0, it will stay in A, Okay. That means no bit has been detected properly, and if x is equal to 1, it will come to state B. That means one bit has been detected properly, right? One bit has been detected properly means still it is not a case of generating the output. So we will discuss about these YOLO circles and all that highlights that, but you do not consider for the time being. Okay. So it is y is equal to 0, right? So when it is at state B, again it receives an input bit, which is x. So if x is equal to 0, okay, so after 1 you have received 0 and you have to detect 1 1 0. So that means you have to start all over again. So it is going back to state A, that is initial state. And if it receives 0, that means 2 bit has been detected properly, received properly. So that is state C. So since it is still 2 states that are detected properly, so it is output is y is equal to 0. Fine. And then at C, again it verifies the input x, whether it is 0 or 1. If it is 0, okay, that means all 3 bits have been properly detected. Okay. So it goes to state D and generates the output y is equal to 1. As long as it is in state D, output remains at 1. Okay. But at state C, if x is equal to 1, so 1, 1, then again you have received a 1. So after that, if you can get a 0, then it will be properly detected. So it goes back to C. It's okay. If 1 is received, it goes back to C. Okay. So this is at being at D, and at that time, if x is equal to 0, right? After 1 1 0, if it receives a 0, it goes to A, because again it has to find out 1 1 0. Okay. Then next bit will be obtained. But if it is receiving a 1, okay, that means first bit of the next sequence has been detected properly, so it is going back to B. Is it fine? So similar to the state transition diagram, but we are following the ASM chart route to get the corresponding diagram for the given problem statement. Okay. Now, if we compare what we can see, that in the state, this was the state transition diagram mood model for this particular problem that we discussed in the earlier classes. Okay. So this is the x, the input that you see here, right? And when it is 1, so this is x, and when it is 1, it is taking this path, and it is going to B, so it is going to B. If it is 0, it is going to back to A, so you can see that it is staying at A. Okay. So this is connected to this x 0 and 1. Okay. And at B, this value was 0, right? Inside the state transition diagram, that circle that we had written, right? Here it is, we are writing in the state box. Okay. So that way it is similar. Okay. And but as I said, if the number of outputs, number of inputs becomes large, so this becomes a bit, 4 such branches will be there. If 2 inputs, okay, then that is not easy to read for state transition diagram based representation. Okay. So ASM chart is preferred for that. Okay. So with this, we come to the conclusion of this particular class. State transition diagram, though compact, is unsuitable for describing large state machine. This is what we have noticed. Okay. ASM chart is a flow diagram like representation, which is useful for designing sequential digital electronic circuit. Okay. To convert the problem statement to a particular chart, which is easier for getting the circuit implemented. So that part we shall take up in the next class. 3 basic components of ASM chart are state box, conditional output box, and decision box. And unlike others, decision box has 2 outputs. So other 2 boxes has got only 1 input and 1 output. So decision box has got 1 input and 2 outputs. Based on the input value, whether 0 or 1, one of the output path is followed. Okay. So, entry into a state is synchronized with the clock, and in Moore model conditional output box is not necessary. There the output is shown within the state box, and in Mealy model output is available through conditional output box. Thank you.